All right, so what we're going to do now is we are going to look at one more example, a little bit more complicated, of nodal analysis, and then we'll talk about some of the interesting things that happen when there are some special, more different kinds of elements in there. In particular, we will talk about the dependent current sources and voltage sources and things of that sort. So again, it would be, we will develop all the cases of the nodal analysis over a couple of lectures. So this is the continuation. So remember, what was the basic procedure for the nodal analysis? If you're presented with a circuit like this, the first step is to define a node as a ground, as your reference potential, right? So again, in this case, you want, and the rule of thumb, not really a rule, but something that would generally help you, is that pick the one with the most connections to it, because you get rid of the largest KCL. So which one would you pick as the ground if you were to choose? The bottom node, right? I mean, so this one would be a good candidate for it, because essentially this is connected to a whole bunch of different things. So that's one, and then you need to define voltages, node voltages. We define V1, V2, and V3. There are three other nodes. There are really four nodes. One is ground. There are three nodes whose voltages we will define. So if you were to write KCL and KVL for these things, we could do, but we also could do, so let me write the case, let's write the KCLs one more time on this and see what happens. So for example, on node 1, let's define this as current I1, current I2, current I3, current I4, current I5. So I'm going to write these this time, and you can try to kind of do it.
Can you use a different color for, like, not the red?
Oh, sure.
Sorry, it's just a little hint.
Yeah, OK. Sorry, yes.
You don't have to erase it.
So let's see. I1, is this better?
Yes.
I2, I3. Is red generally bad or only at this angle?
Probably only at that angle.
But OK, so I'll try to stick with this. V1, V2, V3. So let's write the equations. So for this node, what are the currents leaving the node? We have negative I1, right? Because this is being injected into the node, plus lowercase I1, plus lowercase I2, plus capital I2, this current. There are four things connected to it. It's 0. Right? Is everyone happy with it? There are four things connected. I'm writing those four currents. Here, what about this node? So it's negative I2 because that's entering the node, plus I3, leaving the node, plus I4, plus capital I4, because that's also leaving the node. Right? How about this node? There is, again, I need to put one of those things here. So what are the currents leaving the node? It's negative I4 plus I5, negative I2, negative I3 equals 0. But again, these are not what I'm looking for. What I'm looking for is writing these in terms of the node voltages. So other than the stimuli, I'll have to write these in this. And while I'm doing that, also move the stimuli current to the other side. So I have I1 plus I2 here. So I1 is V1 G1, right? G1 V1, because it's V1 divided by R1, plus, now V1 minus V2, G2. You should convince yourself, if any of these things don't make sense, you should stop me right there. Or ask me why. Equals, now I move these guys to the other side, I1 minus I2. So the second equation is negative I2. I2 is this, so negative I2 is essentially, I can write it as G2 times V2 minus V1. Absorb that minus sign there, plus I3. I3 is what? G3 V2, right? Plus I4, which is G4 G4 V2 minus V3 equals negative I4. I move the stimuli to the other side of the equation. Now, how about this one? Negative I4, right? Negative I4 is what? Is V3 minus V2 times G4 plus G5 V3 equals, I move these guys to the other side, I2 plus I3. So those are the three equations in terms of voltages. You saw what I did? I mean, I'm writing this using Ohm's law in terms of voltages. Right? I'm applying Ohm's law to each one of these things, individual. So this is fine. But now before I kind of like rewrite it as a matrix here, or let's rewrite it as a matrix first. So what are the terms of the matrix? What are the terms that have V1 here? G1 and G2. So it's G1 plus G2. So the second term, which is the terms associated with G2, is negative G2. The third term is 0 because there's no V3 in this matrix. Right? Now, how about the second line, second row? So the terms associated with V1, this is the only term associated with V1. So it's negative G2. Now, how about V2? I have G2, G3, and G4. G2, G3 plus G4. And then how about V3? This is the only term with V3, so negative G4. How about here? I don't have a V1 term, so that's 0. I have a V2 term, which is negative G4. And then I have a V3 term, which is G4 plus G5. Times the vector V equals whatever we have, I1 minus I2, negative I4, I2 plus I3. So let's see if that rule that we kind of like hypothesis that we had about this, how to generate this without writing any of these things, is true. We argued that you could generate this without writing any of these equations, right? So let's see if it's true. So we said that diagonal terms are all the conductances attached to a given node associated with the voltage. So element 1, 1 should be all the conductances attached with this one. So it's G1 and G2. G1, G2, right? The second diagonal term, G2, G3, and G4. The three conductances attached here. G2, G3, G4. The third diagonal term, G4 and G5. Now, off diagonal terms, right? 1, 2 term. The only thing connecting 1 and 2 is R2 or G2, so negative G2. There's no direct resistor connecting V1 to V3. So that's 0. Right? And then between 2 and 3, we have the R4, negative G4. And it's symmetrical. So this seems to be true. And we said, I told you this is true as long as you don't have dependent current sources in there. So that's fine. We can actually make it numerical, and we can solve this. And that's fine. We can write the numerical numbers and all those things. And you will just basically need to invert this matrix again. It's a 3 by 3 matrix. You can invert it, and we could do it at some point. But let's talk about something else. And if there's time at the end, we'll try to invert it. Otherwise, we'll just leave it as an exercise to you. So now, how about dependent sources? We said, OK, well, how about if we have dependent sources, what will happen? So let's look at an example with dependent sources. So now think about, so I'm going to draw another example. So let's say this is I1, R1, R2, R3. And let's say this voltage, so let's say we define this voltage, we call it V pi, sub pi. And we call this G V pi. It really should be lowercase v pi. OK. So what you have here is a dependent source, right? What does that do? I mean, we talked about this briefly before, but it basically says that the current, this is a current source, here is proportional to the voltage across this resistor. So it's a current source whose current is proportional to the voltage of another branch. Hence, it's a dependent current source. Right? So let's write the equations for this and see how they work out. So again, we need to define a graph. By the way, this is not a completely arbitrary, random thing. This is, in fact, you will see it's called a hybrid pi model for transistors. So this is one of the basic models for a transistor later on when you talk about transistors. So this is not a completely useless exercise, per se. So let's define this as the ground, because this is the one that has most things connected to it. Again, we use that rule of thumb. So when we do that, we have two nodes left, right? So we have the, let's call this V1 and V2. Now, if you write it in this form, then this becomes essentially G, capital G, times V1, because V pi is V1, right? The voltage across this resistor is V1 minus 0. So I can express it in terms of V1 directly. Now, if I do that, what do I have? So let's write the equations again. The currents leaving this node, negative I1 plus, let's call this lowercase I1, let's call this lowercase I2, and let's call this lowercase I3. So let's skip the step of writing this in terms of I1 and then expressing them in terms of V's. Let's express them in terms of V's straight. This current in terms of V1, what is that? G1 V1, right? Because it's V1 divided by R1. Plus, what is this current? Is G2 times V1 minus V2. That's the voltage across this resistor. Right? Good? Equals 0. Now, how about here? The same deal. The current's leaving those nodes. So you can write it as G2 V2 minus V1, or negative of G2 V1 minus V2. Okay, what else do you have? You have G3 V2, which is the current through here, that resistor. You have one more current, which is what? This dependent current source, right? Which is what? Let's call it GM. G sub M. GM V1, right? That's the current. And it's written in terms of V1 or V2. So these are the two equations. So if I translate this to rewrite them in terms of matrix form, what do I get? All the terms that have G1, I get G1 plus G2. Then I get negative G2. Then here, what do I get for V1? I get negative G2 from here. But I get one more thing, this term. Right? So I get negative G2 plus GM. And for G2, for V2, I get G2 plus G3. So you can see now that the Y matrix becomes asymmetrical when you have dependent sources. It's essentially that old Y matrix, but it has this extra term here. So again, you can come up with heuristic or simple ways of coming up with them, but you have to keep these things in mind. So that rule doesn't apply by itself anymore. I mean, you have to think about these things. And again, it's applied to vector V, and the stimuli vector, again, is the same thing, I1 and 0. So that's the situation. When you have dependent sources, there's nothing fundamentally different, except for the fact, so the process and the algorithm is applied the same way. The only thing is that now you have asymmetrical ones, and you have these additional terms associated with these dependent sources, depending on what they depend on. Right? So that's the way those things work. Any questions on this? Yes?
How do you get a dependent source?
How-
Dependent on something it's not connected to.
How do you make it? Is that the question? Okay, so you're asking a physical question. It's a good question. So you should say, okay, well, yeah, this is a mathematical abstraction, but how do you make something like that? There are different ways to do that. I could turn the question back around and say, well, how do you even make an independent source? And then you can say, I make it with the battery. Say, well, okay, why don't you can have something that looks at changes the value of the battery but that's not a good answer. That's not a really fair answer, right? There are devices for example, a transistor is exactly what it does that for you. A bipolar transistor, for example, is modeled best as a voltage-dependent current source. Now, what happens, the physics of it inside is quite sophisticated, and you can learn it in 114, for example, or 4D. You will learn some of that physics. What you do, and different transistors have different physics. So this is done using different physical mechanisms. BJTs do it one way. MOSFETs do it another way. One way to think about it, MOSFETs are probably easier to kind of like articulate in a couple of sentences. Think about a piece of semiconductor whose conductance is related to how many electrons are in a certain part of it, what we call the channel. If I apply electric field to it, I can get more or less electrons in that channel, or charge carriers. So that's the gate. That's this terminal, controlling it. If that terminal, if I increase the voltage on that, what happens is that I get more charge carriers inside the channel, which means my resistance is going down. So I produce a smaller resistance. So that can carry more current. So that's one way to approximate this, for example. Again, there's a lot more to it. It's basically, you will learn it in 4D, 114, things of that sort. So that would be the subject of those kind of things. But this is really the essence of it, is that you control a physical property which controls the resistance or the current or the voltage of something. So, but yes, you can make things that are having this kind of property. You can even think about a mechanical contraption that does this, right? I can make some kind of like, this is like going to be crazy stuff. I'm just making it up right now. So let's say you have a voltage here, right? You apply it to a plate, okay? And then this plate is attached to another plate. So this is the charge plate. This is a negatively charged plate. And it's attached to some sort of a spring against the wall. And then as you apply this pulls on a variable current source. It's like a potentiometer that changes. It's that. So as you apply a larger electric field, it attracts this pulls this forward, it starts pulling on this. You can actually make it like a variable resistor, even like that. Right? As you apply it, just like you pull it in and then you just push it out. So this becomes, if this is the dependent source, if you will, and this is the independent source.
So isn't that essentially adding an element between the voltage and the...
Yes, correct. It is an element. In fact, this is the transistor. This is its base or gate. This is its emitter or source, and this is its drain or collector or a vacuum tube or anything. There are lots of different kinds of devices that can be modeled this way. Yeah. But good question. Great question. Okay, any other questions? Yes?
Why did you put the ground on the wire?
Why did I put the ground on the wire? You mean here? Yeah. Well, I basically said, the way I was thinking about it is that this entire thing is a node, right?
Oh, okay.
Right? So it doesn't matter where I connect it. I'm attaching this, I'm making this node ground. So this is a convention of the way I draw circuits. Yeah? Yes, in the back.
How would you do this analysis if you had like a constant voltage source?
Oh, okay, that's a good subject. We will discuss that in the next lecture. That will be the subject. Yeah, we'll get there. It's a good question. You will define a supernode. Short answer, it doesn't mean anything. It's just like throughout the loop. That is correct, but it doesn't mean anything until I tell you what a supernode is. But, all right, so there's one more thing I want to actually go over before we finish for today. So the question is, so far we've seen that, okay, you can define a matrix and then you can get these things solved that way. But how do you know that there's an answer? How do you know that the solution exists? So this is the equation you're solving, right? You're saying that y times v is I stimuli. But then the question is, when do I have a solution and when I don't? So when can I find v unambiguously by doing this? Yes?
When y is non-singular.
When y is non-singular, when you can invert it, which basically means another way is, what can you say about it in terms of its determinant? Determinant is non-zero, right? So if you have a determinant that's non-zero, you can basically invert it. So the question is, this is a mathematical thing. Can we translate it to a circuit characteristic, something that we can look at a circuit and say, this circuit does have a solution or this circuit does not have a solution? Can we convert this? And this is where the Y matrix analysis formation comes into use, because you can actually think about these inverses as entities and play with them and come up with results. So let's ask you this question. So if the determinant of y is not 0, that means that the solution to, if we get rid of the I, the solution to y, v, right, equals 0 is always that v is identically 0. These two things mean the same thing. As long as the determinant is non-zero, it means that you can invert this, right? And if you can invert it, it means that you can actually calculate v by applying the inverse to 0, which gives you 0. The vector 0, right? So it's, as long as the determinant is 0, the solution to this should be identically 0. And the only time the solution to the vector v, so if you can have v not equal to 0 with y v being 0, then you can be sure that the determinant must be 0. Does this make sense? I'm saying that the only way yv can be 0, and this is if this is invertible, the only way this is true is for v to be 0. And if v is non-zero, a solution to this, if there exists a non-zero solution to this equation, that means, therefore, this is the exact conclusion from this, that determinant must be 0. So we should look for situations where you can have, if you want to find cases where they cannot be inverted, you should look for situations where the v is not 0 when you have no stimuli. Because when you set this to 0, it means that you have no stimuli. No stimulus whatsoever, right? If you don't have any inputs, if you set all of your independent currents, not dependent ones, independent ones, null them, set them to 0, and you can still have a solution that where v can be non-zero, then it means that this is not invertible. So let me show you an example, just to show you what I mean, what this means. Think about this circuit. So let's think about this. So resistor R1. I mean, there are several examples, so this is like a simple one. So let's say this current is I1 and this current is I1 too. So they have the same value, right? So this is an acceptable situation. We define a node as a ground. We define this node as ground. So how many nodes do I have left? 2 or 3? V1, V2, V3, right? So let's write the nodal equations. I mean, we don't have dependent sources, so we can actually use our rule of thumb quickly right here. So what we can do, so the Y matrix, element V11 is going to be G1. Element V22 is going to be G2, and element 3 is going to be G2 as well. The one connecting V2 and V3 is negative G2 and negative G2, and everything else is 0. So that's times V1, V2, V3, and then you have the stimuli vector, which you can write, but we don't need. So now let's see. First of all, let's look at this from a physical standpoint. If I set all the stimuli to 0, in other words, if I set the vector to be 0, the IS vector to be 0, it means that I have nulled all my independent sources. I've made them 0. What does it mean to make a current source? What does it mean to make a voltage source 0? What do you turn it into? We talked about this last time. It's a short circuit, right? A voltage source whose value is 0 is short circuit. What is a current source whose value is 0? It's an open circuit, right? So when I do that, I essentially am taking this out and this out, right? So this is 0 potential by definition. If this is 0, if there's no current flowing through the resistor, what is the voltage across the resistor? 0 voltage. So what is V1? Identically 0, right? So far, no problem. How about V2 and V3? Can you say V2 and V3 are identically 0? No. There's nothing to enforce that condition. They're just two nodes floating. They're the same voltage. You can say that V2 is equal to V3, but you can't say that they're both equal to 0. They can both be equal to 5 and nothing will happen. Then there's nothing wrong. If this is 5 volts and this is 5 volts, there's no contradiction. There's no problem. They can be 3 volts. They can be negative 1,000 volts, right? So this happened, right? We had a situation where we forced this. We made all of our stimuli 0. But we had a situation where V was not equal to 0. So let's see if the determinant of this thing is 0 or non-zero. What is the determinant of this thing? Is this times the determinant of this guy, right? Because these two are 0. What is the determinant of this guy? G squared minus G squared, right? So the determinant of Y is 0 in this case, which means that there is no unique solution. So what is the process for when you're looking at a circuit? You set all your independent sources, not dependent sources, independent sources to 0. There's an expression for it. We say we null the sources. We null all our sources, and then look to see if a solution where any of the voltages is non-zero can exist. If that exists, it means that that circuit is singular. That Y matrix, associated Y matrix is singular. It means that the determinant of Y is 0. It means that that linear transformation transforms in such a way that it cannot be inverted. It collapses multiple points to one point, right? So there are different ways of saying the same thing. So what happens practically when something like this goes on, right? So let's talk about an example here briefly. Going back to our, again, basic linear algebra. So let's say, you may say, what do you mean? So let's say I have something like this. So if I have 2x plus y equals 5, right? And if I write, so when you write two equations and two unknowns, another interpretation is that you have two lines, right, in the xy plane, and you're trying to find the intersect point, right, when they hit each other. So what if I wrote like 4x plus 2y is 10, right? You know, when I was actually first introduced to the two equations, two unknowns, I don't know, like 12 years old. I said, you know what? And I was actually fascinated by the fact you can actually solve for one of these things and put it in the other one. I said, okay, you know what? I can even solve one equation, one unknown, because I can solve for this y and put it back into this equation. And eliminate y, then I get one equation, one unknown, so I can solve it. And you know, I tried, and this is what I got, right? So if you do this, you say it's 5 minus 2x, plug it back in, so you get 2x plus 5 minus 2x equals 5. I got 5 equals 5. So okay, very, very useful, right? And so now you can make this any number, right? I mean, so if this would let's make this. If I make it 10, it's the same equation exactly, right? So that obviously is not very useful for me. What if it's a different equation? Right? This is clearly a case where the determinant is 0, right? You have a 2, 1, 4, 2. Right? So let's see what happens. What happens if I try to solve these two equations? The same way, the very simplistic way of solving for one equation, for one unknown and putting in the other one. So if I use the same thing that they just erased and plug it back into this guy, what do I get? I get 4x minus 2 times y, which basically gives me 10 plus, no, wait a second. I made a mistake. 5 minus this x, 4y, 2y. Say again? You're confusing me. Too many. So, okay, let's do this. Y is 5 minus 2x. Okay. 4x. Okay, that's the problem. Yes. 4x plus 10 minus 4x equals 12. Right? And 4x is cancel and I get 10 equals 12. Nice. Right? That's what happens. Now, what does this mean? What happened from a perspective? If this were 10, what would these two lines be? The same line, right? I mean, so you can actually find, I don't know what, you can find what that line is, some line like this. Right? But now, if it's 12, if you have a different number, what you're doing essentially are defining two parallel lines. And that's why you're getting 10 equals 12. Basically, that means that this is singular matrix. That means that there's no solution for this. That means the determinant is 0. That means all of those things. There are different ways of thinking about the same thing. All right. So with that, so we found a condition for finding what the general solution exists, whether or not the general solution to nodal analysis exists or not. So next, what we'll do, we'll talk about cases where you have voltage sources. We'll talk about expand it a little bit more. And we'll talk about mesh analysis, which is the dual of the nodal analysis. All right.